Now, we can classify collisions. There's three different types of collisions. We've got elastic collisions, inelastic collisions, and perfectly inelastic collisions. Let's start by considering an elastic collision. In an elastic collision, as in all collisions, momentum is conserved. But an elastic collision is special because kinetic energy is also conserved. So a great example of an elastic collision is with a Newton's cradle. So let's have a look at that now. What we've got here is a device known as a Newton's cradle. This is a really nice demonstration of elastic collisions. If I pull one ball up on this side and release it, the momentum is transferred through all these balls to the one at the end, which then rises to approximately the same height as this ball was initially. Now what gets really interesting is if I pull two balls up on this side, you can see that two balls rise up on the other side. If we do three balls rise up on the other side. Four balls. And even five balls. So let's now try solving a problem using the Newton's cradle. So we need to show that if one ball is swung down in the Newton's cradle device and two balls end up swinging up, then the collision is not elastic. So let's draw a diagram. We've got one ball, mass m, with some initial velocity vi coming down, and then we end up with two balls, each of mass m, with velocity vf swinging up. So each of these balls has velocity vf. So we know that in a collision momentum is conserved. So we know that the initial momentum is equal to the final momentum. And so the initial momentum is just the mass times the initial velocity, because all the other balls are at rest to start with, and then at the end we've only got these two balls moving, so we've got 2m, that's the total mass because there's two of them, times the final velocity. So that's what conservation of momentum tells us. Now, if kinetic energy is conserved, then we've got the initial is equal to the final kinetic energy, and the initial kinetic energy is given by a half mvi squared, and the final kinetic energy we've got half, and then we've got 2m, and then we've got vf squared. So let's rearrange this equation and make vf the subject. So we've got vf is equal to mvi over 2m, and so this is equal to vi on 2. And now what we're going to do is replace the vf here with this expression and see what we get. First of all, note that the halves on either side of the equation cancel and the m's cancel as well. So we've got vi squared is equal to 2 times vf squared, which is vi on 2 all squared. So this is equal to 2 times vi squared on 4. So this is equal to vi squared on 2. But we can't have vi squared is equal to a half vi squared. Unless the initial velocity is 0, that is impossible. So as vi squared does not equal vi squared on 2, this is not possible. So as kinetic energy is not conserved, this collision would not be elastic. So let's go and look at what happens when we have a collision which isn't elastic now. An inelastic collision is one in which momentum is conserved, as it is in all collisions, but kinetic energy is not conserved. So an example of an inelastic collision is a car crash. During a car crash, the metal making up the cars deforms. There's also sound and heat energy lost. So you need energy to deform the metal. And so some of that kinetic energy is lost to other forms of energy. Let's solve a problem now involving an inelastic collision. So the question is, a car crashes into a wall. Before the collision, the car is travelling with a velocity of 60 kilometers per hour towards the wall. After the collision, the car is moving away from the wall at 20 kilometers per hour. And the question is, part A, is the collision elastic? And part B, is momentum conserved in this collision? Explain. Okay, so let's draw a diagram of what's happening. We've got a wall here, and here's our car travelling towards the wall at 60 kilometers per hour. And then afterwards, we've got our wall and we've got our car moving away. Should be a slightly shorter arrow. Let's make it a bit shorter. At 20 kilometers per hour. Now, is the collision elastic? And the answer to that is no. Kinetic energy is not conserved. So we've got initially kinetic energy equals a half times the mass of the car times the initial velocity of the car squared, and the initial velocity of the car is 60 kilometers per hour, and 60 kilometers per hour is equal to 60 times 1,000 over 60 times 60. So this turns out to be 16.67 meters per second, and down here the final velocity is 20 kilometers per hour, which is equal to 20 times 1,000 over 60 times 60. So this is equal to 5.55 meters per second. And so this is equal to a half times whatever the mass of the car is times 16.67 squared. And then finally, the kinetic energy, it's mainly in the car. The wall will be moving backwards a little bit and it's attached to the mass of the earth, but that velocity is much smaller. So we've got a half times the mass of the car times 5.55 squared plus the kinetic energy of the wall. But this is very small because the velocity of the wall is very small and the kinetic energy is proportional to the velocity squared. So kinetic energy is not conserved. It will be lost through energy going into crumpling the car, etc. Now part B says, is momentum conserved in this collision, and explain. Okay, now this one isn't so obvious. The answer is yes, because momentum's always conserved in a collision. But what's happening is the initial momentum is equal to the mass of the car times the velocity of the car, which is the initial velocity of the car, which is 16.67 meters per second. And the final momentum is equal to, now the car is moving in the opposite direction, so it's the mass of the car times 5.55, but this is negative, plus the momentum of the wall. Now the wall does actually have momentum. Even though it looks like the wall is fairly stationary, the wall is connected to the earth here. So the wall and the earth do move backwards a very little bit when the car hits it. However, because the mass of the earth is very, very, very large, the velocity is very, very, very small, and so you don't actually observe this movement. So momentum is conserved. Now, if you wanted to show part A little bit more mathematically, you can take some time and prove that for an elastic collision, the initial velocity of object 1 minus the initial velocity of object 2 is equal to negative the final velocity of object 1 minus the final velocity of object 2. Now in this case, the initial velocity is 60 kilometers per hour and 0, so this is 60, and the final is 20, and we've got very close to 0, so around about 20, so clearly they're not elastic. But this equation holds for elastic collisions. You show it by solving simultaneously the equation for conservation of momentum and the equation for conservation of kinetic energy for two objects colliding.
Now we use this Newton's cradle to demonstrate elastic collisions. We can actually force it to be an inelastic collision if we use some blue tack to stick some of these balls together. In this case, if I hit it with one ball, the three balls at the end are forced to move. Or if I just have two balls, the two balls at the end are forced to move. And we've shown that in this case, that can't be elastic. In a perfectly inelastic collision, momentum is conserved and kinetic energy is lost, except it's different from an inelastic collision because the two bodies which are colliding end up stuck together. So initially they're travelling separately, and then at the end they're travelling together. So let's have a look at an air track now, where we can model these different types of collisions. So here we have a demonstration that should show a perfectly inelastic collision. What we've got here is an automated golf club to make up for my poor golf skills. It's going to hit the golf ball down here. The golf ball is going to travel over to this cone over here where it should remain trapped, and the golf ball should stay in the cone so that they move together, so that this is a perfectly inelastic collision. Okay, let's see if this works. Yep, so that is a perfectly inelastic collision, as after the two objects had hit each other, they remained stuck together. Okay, so we're going to have a collision here. I'm going to let go of these balls. Now, as you watch the collision, I want you to think about whether momentum's conserved, and the tricky one is kinetic energy conserved.
So both momentum and kinetic energy are pretty much conserved in this collision. Initially, the big ball and the small ball have the same velocity downwards towards the ground. After they hit the ground, the small ball is travelling very quickly and the larger, heavier ball is travelling more slowly. But overall, the kinetic energy has been conserved.